So determine first one, input impedance. Second one, output impedance. Third one, voltage gain. Okay, so voltage gain you need to determine with bypass capacitor and without bypass capacitor. And also you can determine the current gain as well. Current gain. Okay. This is beta RE. Beta IB. Since we are considering, with bypass capacitor, what happens is that emitter will be at ground potential, right? And this is our collector resistor. And they have also given the load resistor. RL, check here. RL is given. Hence, you have to place RL as well. All right. On the input side, what do you have? On the input side, you have the voltage divider bias resistor combination, right? That is R2 and R1. It's getting connected in parallel. Okay. And this is where you give your input, and this is where you take out your output. All right. So that's your RE model with bypass capacitor. Okay. Now, let's start finding out the performance parameters. Zi on the input side, Z0 on the output side. All right. Fine. So first, let us find Zi. Okay. So what is Zi? Zi is the input impedance observed from the input port, right? So when you look into the input port, you see that the three resistors, connected in parallel. They are R1, R2, and beta RA. You know the values of R1, R2, okay? And beta value is also known. The unknown is RE over here. So RE is given as 26 millivolt divided by DC current IE, okay? So we don't have IE relation, right? We don't have IE relation, but we know IC. So given, IC as 2 milliamperes, and also given beta as 100. So that will enable us to find out the base current, IB. So IB is IC by beta, 2 milli by 100. I guess that is going to be 20 micro. Okay. Yeah, it's 20 microamperes. So IB is equal to 20 microamperes. Therefore, your IE becomes IC plus IB. Okay. So that is 2 milli plus 20 micro. Okay. So that's 2.02 milliampere. So that is your emitter current. Okay. So then your RE becomes 26 milli divided by 2.02 milli. So that is 12.87. Are you getting it, guys? 12.87. Okay. And therefore, beta RE is 100 times 12.87. So that's 1287.12. 1287.12 ohms. Okay, so therefore Zi becomes 47 kilo ohm parallel with 10 kilo ohm parallel with 1.287 kilo ohm. All right, so how much you'll get? Did anyone calculate? Okay, so that's your Zi. Okay. Now let's go to the second part, the output impedance Z0. Okay, so output impedance Z0 is the impedance observed from the output terminal. So when you look into the circuit from the output side, you see that between collector and ground, two resistors are coming in parallel, and those two resistors are RC and RL. So Z0 becomes RC parallel with RL. All right. So what is the answer? Tell me. So RC is 2.2 kilo ohm parallel with 1 kilo ohm. So Z0 is 687.5 ohm. Are you getting this? Can anyone confirm? Okay, so that's your Z0. Okay, remember everything I am considering with bypass capacitor. Okay, with bypass capacitor I'm considering part A. Okay, so that's your Z0, and then let us go for voltage gain AV. Okay, so voltage gain AV. Okay, let me write with bypass capacitor C is given by the expression. It is basically, let me rewrite. Okay, minus IC into Z0 divided by IB into ZB, right? And that is equal to minus IC into Z0. Z0 we have already found, right? 687.5 divided by IB into ZB, right? What is ZB? Other day we have seen ZB or ZI. Yeah, there is no ZB here, okay, which is ZI itself for a bypass capacitor series. Okay. Okay, so that's beta RE itself, and IC by IB, anyhow you will get it as beta. So this beta gets cancelled, hence you are left with AV with CE is equal to negative 687.5 divided by RE. And how much did we get? RE as 12.87. Okay, so your gain is negative 687.5 divided by 12.87. That's about
53.41.
53.41. Okay, you'll be surprised now to see the effect of bypass capacitor. Okay, so here itself, let me consider part B. Okay, part B, and in part B, what we will do, we will recalculate AV, but without bypass capacitor. Okay, so in the previous class we had seen that without bypass capacitor, the voltage expression, voltage gain expression becomes minus RC parallel with RL. Okay, because there is load resistor, hence I am considering RL. If there is no load resistor, you can go for just RC. Let us include that part as well. Divided by, what is it? Small RE plus capital RE. Okay, so that gives your voltage gain as minus RC parallel with RL is nothing but Z0. So 687.5 divided by RE 12.87 plus capital RE, the biasing resistor, which is 470 ohms. Okay, so that gives AV, without C as, did anyone calculate?
Minus 1.4237. Minus 1.4237.
Okay, 4237. Okay, 43. Okay, minus 1.43. Okay. Just compare these two results. Okay, this is what happens even in lab as well. Okay, sometimes what will happen when you rig up this RC coupled amplifier, okay, this particular amplifier, by mistake the capacitor connection may not be the capacitor may be loosely placed inside the breadboard. So when there is, it will be considered as without bypass capacitor condition. So if so, an amplifier which is expected to give a gain of 50, ends up giving a gain of almost 1.5. Okay, so you can see the effect. A small capacitor, causes such a huge difference. Okay, so you have to be very careful when you execute the RC coupled amplifier circuit. Okay, so that's your voltage gain. Okay, now whatever voltage gain we have calculated, is it no load voltage gain or loaded voltage gain? Can anyone tell me? This is called as loaded voltage gain. That's because RL is considered. Okay. You are studying transformers, right?
Yes, sir.
Yeah, okay, fine. So in transformers, you must have come across something known as voltage regulation, right?
Yes, sir.
We say change in secondary terminal voltage from no load to full load. Okay. So in transformers, which voltage is more, no load voltage or full load voltage?
No load.
No load voltage. So though we are studying, analog electronics, the concepts won't change. Even in, AEC, the no load voltage, or rather no load voltage gain, should also be, bigger than the loaded gain. Let's see. So let me just consider an exceptional case here. Okay, though it is not the part of the main problem, I'm just considering it as an exceptional case here. Okay, so just take down, calculate the gain without RL or without load. Okay, calculate. Let me write voltage gain itself. Calculate voltage gain without RL. Okay, for bypass capacitor case. Okay, let's consider bypass capacitor only. This is just to understand the effect of no load. Okay, so AV is minus V0 by Vi, or minus I0 into Z0 divided by IB into Zi. Okay, or sorry, IB into, directly you can write beta Re. Okay, so I0 by IB. Okay, so your I0 is anyhow IC, so that's beta into Z0. Okay, what is Z0 when you don't consider RL? It is only RC,
RC.
right? Divided by beta Re. So AV, okay, you can call it as AVNL. AVNL stands for no load voltage gain, is simply the ratio of collector resistor to AC effective resistance. Okay, so that's minus 2.2 K divided by 12.87, and see how much you'll get it. So 2.2 divided by 12.87. So that's about 170.94. Correct, no?
Yes, sir.
Yeah, 170.94. So what is its effect? Okay, say say your input signal is 15 millivolt. Okay, say your input signal is 15 millivolt. If you consider an amplifier with a loaded gain, okay, this is loaded case. So for loaded case in AEC, normally we take the voltage gain as a simple A. Okay, so let's feed input which is equal to 15 millivolts. Okay, so the loaded gain, how much did we get? We got the loaded gain as 53.41, right? So this loaded gain is 53.41. So your input signal is scaled up by a factor of 53 units. So 15 millivolt signal becomes roughly, 801 millivolt. So your output, okay, will be at 801.5 millivolt. Okay, so that's how the no load case works out. Okay, on the other hand, if you consider, sorry, this is the loaded case. On the other hand, if you consider the no load case, what happens is that when you feed the same signal, okay, having a maximum value of 15 volts, will appear, a much larger way, right? The signal will appear in a much larger scale. So the multiplication factor for output, it becomes 170.94. So 15 into 174.94.
2564.
Yeah, 2624. Yeah, so that's about 2624.1 millivolt. Okay, you can make out. Okay, so this is your basically no load voltage, and this is your full load voltage. So basically, you can calculate the regulation for analog circuit as well. Okay, fine. So this is the thing. Okay, and you need to calculate the current gain. Okay, current gain can be calculated as the voltage gain into Zi by Z0. Okay, the previous class we have taken. So let's consider the loaded gain here. So loaded gain is 53.41 into Zi. So Zi is 1.1, roughly 1.1 kilo ohm, I guess. Yeah, 1.113 kilo ohm. Come down. 1.113 kilo ohm divided by Z0. So for loaded case, your Z0 was 687.5, okay, ohms. And take out the ratio. Let's see how much we get. Are you getting current gain as 86.46?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So this is one thing. What you have to understand over here is that your current gain of the transistor, okay, beta is 100. So current gain of the transistor is 100, but in your real circuit, you get about 86.46 units of current gain. So that's how you have to compare. Okay, all right. beginning I mentioned, common emitter configuration always gives 180-degree phase shift between the input and the output. Phase shift between Vi and V0. Okay. So approximation. Okay. So in approximation, you have already seen that if your R0 is 10 times greater than RC, you can write RC parallel with R0 approximately RC itself. So your approximate, voltage gain expression can be written as minus RC divided by RE. RC divided by RE. Okay. And if load of RL is connected across the collector to ground terminal, then AV is given as, can anyone tell me, if a load of RL is connected across collector to ground terminal, then what would have been the gain? Can anyone tell me? It's something like this. Just redrawing the output circuit scenario. Okay. So this is your beta IB. Okay. So this is your R0. This is your RC. Okay. So what I'm saying is, let's say load resistor RL is connected, okay, across collector and ground. Then what will be the expression for voltage gain? Can anyone tell me? What will be the expression for voltage gain? What is V0? V0 is always minus I0 into Z0. And what is Z0 here? For Z0, you have 3 resistors connected in parallel. So Z0 going to be R0 parallel with RC parallel with RL. Yes. So this is how we calculate. Okay. You don't have to worry about what kind of resistance is connected. Is it a small resistance or large resistance? Doesn't matter. Okay. It is always going to be a parallel circuit across the output side. So basically 3 resistors gets connected in parallel. Okay. So that's how we calculate the gain. So your voltage gain, exact expression for voltage gain going to be minus R0 parallel with RC parallel with RL divided by RE. So this will be the expression if you have any load connected across collector and ground. Okay, fine. So that's your voltage gain. And finally, we have our current gain AI. So current gain AI is given as I0 by II. I0 by II. Okay, where I0 can be extracted from your output voltage expression, right? What is I0? I0 can be given as minus V0 by Z0, because we have already seen V0 is negative I0 into Z0. So I0 is minus V0 by Z0. Okay. And that can be written as minus V0 divided by, what is Z0? Okay. Z0 is RC parallel with R0. Okay, I'm not considering the load resistance. If load resistance is there, you can also include RL over there. All right. Right. And also we have II. II is nothing but input, voltage divided by input current. Okay, fine. So let us find, AI. AI is I0 by II. Okay, what is I0? We have minus V0 by Z0 into II. What is II? It is basically Vi by Zi. Since it is coming in the denominator, it is Zi by Vi. Okay, now let me rearrange the expression in such a way that I get the voltage ratio. So V naught by Vi, okay, into the ratio of two impedances, Zi by Z naught. Okay, Zi by Z naught. Okay, so what is this expression? Can anyone tell me? V naught by Vi. What is this expression? This expression is the voltage gain, output voltage to input voltage. Okay, so negative V naught by Vi is AV. So what you can write is, you can write your current expression as AI is equal to AV times Zi by Z naught. Okay, and remember the current gain is dimensionless because voltage by voltage unitless, the impedance by impedance again unitless. So this is dimensionless. Okay, that's how we calculate the current gain. So current gain can be simply calculated by taking out the impedance ratio, input impedance to output impedance divided into the voltage gain. Okay, Zi and Z naught is already being found in the previous steps. Okay, all right. So this is the concept of calculation of performance parameters. Okay. All right. Now what let me do is, let me quickly solve a problem on common fixed bias circuit. Yeah, all right. Take down the question. For the network shown below, determine the following. RE, Zi with R naught equal to infinity ohms. Third one, Z naught with R naught equal to infinity ohms. Fourth, AV with R naught equal to infinity ohms. Okay, fifth one, Z naught and AV with R naught is equal to 50 kilo ohms. 50 kilo ohms. Okay. And compare the results. Okay, so this is the circuit. Okay, so R naught is given 50 kilo ohm, RB is 470 kilo ohm, RC is 3 kilo ohm, and this is the base, collector, and emitter terminal, and you also have been given with the capacitor values, 10 microfarad each. All right. This is your Vi, and this is your V naught. Okay. All signal measurement is done with respect to ground. Okay. Whether they show ground terminal or not, you should understand that Vi and V naught is always measured with respect to either base and ground or collector to ground. Okay. Fine. So this is the circuit diagram. This is the circuit diagram. Okay. So first we need to construct the RE model. Okay, remember one thing, this particular question can be asked with emitter bias or voltage divider bias. Okay, the method remains the same. Normally this particular question comes for 8 marks to 10 marks. Okay, so this is how the marks are distributed. Okay, first you have to construct RE model. So this RE model will get about 2 marks. All right. So RE model you construct. You don't have to write down these steps, okay, such that ground VCC, short circuit capacitors. Directly you can apply those steps. So what I will do, I will short circuit the capacitors. SC is short circuit the capacitors. Okay. Next, ground VCC. Okay. And then let me reconstruct the circuit. Okay. Then let me just redraw the circuit. Okay. So this is what you get when you redraw the circuit. So this is your base terminal. This is your beta RE. Okay, I'm just placing the RE model also. Okay, this is your beta RE. And then comes the external biasing resistor, RB. Okay. So this is where you feed your input, Vi, minus and plus. This is your II, and this is your IB. So that's on the input side. And on the output side, you have the controlled source, beta times IB. Okay. And the collector terminal. Okay. And you will also have the output impedance of RE model, small r0, and then the collector resistor, okay, RC. Okay, so RC is 3 kilo ohm. Let me write down the value, and RB is 470 kilo ohm. All right. So this is my RE model. So what I will do to add, better clarity, let me place the RE model element inside this box. Okay, this is my RE model for CE mode, common emitter mode. Okay. Did you understand? Can I go ahead?
Yes, sir.
So this is my V0. All right, fine. First one, let us find out RE. So first task is to find effective AC resistance RE. So RE is calculated as 26 millivolt divided by, IE. Okay. So this IE, I have already told you. Okay, I capital, E capital, right? So this is DC current. Okay. So how will you find DC current? You can find DC current provided you know the biasing circuit, right? Now we have already seen in module 1 that for a fixed bias circuit, your base current IB is basically VCC minus VBE divided by RB. You see, module 1 will not leave you until you reach module 5. Okay, till module 4, you will be pulling the concepts from module 1, module 2, so on and so forth. Okay, fine. So IB is this. Okay, once IB is known, you can find out IB, correct? So IE is 1 plus beta times IB. So this is the whole idea behind calculating IE. Okay, so what's VCC? VCC is, let me go up, okay, 12 volts, right? So VCC is 12 minus VB, given or not given, let us assume silicon transistor, divided by RB. RB is 470 kilo. Okay, here I want to make a point. If given, you take the respective, transistor, whether it is silicon or germanium. If not given, always assume silicon transistor. Okay, don't become aggressive and don't take your germanium or gallium arsenide. Okay, because in the scheme, almost all the times they will take the VBE potential as 0.7. Okay, so please take it as silicon if the type of material is not mentioned. Okay, so what do you get IB as? Okay, IB, do you get closer to 24 microamperes? Did anyone get it? Are you getting it? Nirja, are you getting it?
Yes, sir.
Okay, fine. So IB is 24, and what is IE? So it is 1 plus 100 into 24.04 microamperes. So it is about 2.4 milli. Okay, so 2.428 milli. So IE is 2.428 milliamperes. Milliamperes. Once IE is known, you can find out RE. RE is 26 millivolt divided by IE. That is 26 milli divided by 2.428 milli. 10.71 ohms. 10.71 ohms. So that's your RE. Okay. Let us cut it off. So RE is formed. Okay. So this step will fetch you, say, 2 marks. Okay. Next we have ZI. Okay. So you need to determine ZI with R naught is equal to infinity ohm. Okay, trust me, R naught is found on the output side, so it will not have any effect on ZI. Okay, this is just to confuse you guys. They have given find ZI under the impression that R naught is infinite ohm. Doesn't really matter because ZI is found on the input side. So what is ZI? ZI we have already seen in the previous analysis that ZI is parallel combination of RB and beta RE. Yeah, so this is ZI. Let me mark. Okay, as you when you look into the network, you get to see the ZI. Similarly, on the output side, when you look into the network, you would get Z0. Okay, so ZI is RB into beta times RE. That is equal to, okay, RB is 470 kilo ohm. Okay, into beta is 100 into RE is 10.71. Okay, divided by 470K. Okay, plus 100 into 10.71. Okay, beta is 100 and RE is 10.71 ohms. So how much will you get ZI as? Because you can clearly observe that RB is very, very big compared to, you know, beta RE. So obviously your beta RE, sorry, ZI should be very close to beta RE. By inspection method only I can tell. You just find out and tell me what do you get overall input impedance ZI as. I think you'll get it as 1.07 only. Correct? Can
Yes,
anyone?
sir.
Yeah, quickly confirm. Yeah, fine. So that's your ZI. Okay, you can see that. Let me write proper comment over here. Very close to beta RE. Okay, that implies your ZI is approximately close to beta RE. This is what we had predicted, right? If your RB were to be 10 times greater than beta RE, then your overall input impedance will be very close to beta RE itself. Okay, this is what is the end result. Fine, so that's your ZI. Next, third one, what is it? Z0 with R0. Okay. Z0 with R0 is equal to infinity ohms. Okay, Z0 with R0 is equal to infinity ohms. That means to say, okay, first let me write the exact expression for Z0. So Z0 is RC parallel with R0. Okay, Z0 is RC parallel with R0. So that implies 3 kilo ohm is connected in parallel with an infinite ohm resistor. So what is the output impedance then? Can anyone tell me? 3 kilo ohm itself. Okay, 3 kilo ohm itself. So output impedance is 3 kilo ohm. Why is that so? Because when you have two resistors connected in parallel, One is having low resistance value and one is having extremely high resistance value. What happens is that current flow through this infinity ohm resistor is 0. So it gets isolated from the circuit. Hence, you will be left with only the finite resistance resistor, which is 3 kilo ohm resistor. So that's your Z0, third one. Okay. And fourth one is AV, okay, with R0 is equal to infinity ohm. Okay. So expression for AV, okay, let me just rewrite the expression, is minus I0 into Z0 divided by IB into ZI, or minus I0 is IC and Z0 is RC parallel with R0 divided by IB into beta RA. Okay, so you know that IC by IB is beta. So this beta and this beta gets cancelled. So AV is minus RC by R0, sorry, RC parallel with R0 divided by RE. Okay, so we have already seen that when you have an infinite ohm resistor connected across RC, your output resistance becomes RC itself. So basically voltage gain in this particular case going to be the ratio of collector resistor to AC effective resistance RA. So that's minus 3 kilo ohm divided by 10.71 ohms. So how much will you get? AV as around minus 280.11 you will get. That's the textbook answer. So that's your voltage gain under infinite output resistance. Okay, now let us find out. Okay. Fine, fifth one? Yeah, fifth part. Right, fifth part. Yeah, fifth part, what is that we should do? We should find Z0 as well as AV with R0 is equal to 50 kilo ohm, right? So let's find out Z0 with R0 is equal to 50 kilo ohm. Okay, what will happen if you take a reasonable amount of output resistance? So Z0, okay, once again is RC parallel with R0. Okay, that implies RC into R0 divided by RC plus R0. 3 kilo plus, sorry, 3 kilo into 50 kilo divided by 3 plus 50 is 53 kilo. Okay, so you would get Z0 as how much? How much you will get Z0?
2.83 kilo.
Correct, no? 2.83 will get, right? Okay. Okay, good. So, you know, since they have asked you to compare the value, so you can say that with R0 is equal to 50 kilo ohm, Z0 is reduced. Okay, that is not appropriate. Z0 gets reduced from 3 kilo ohm to 2.83 kilo ohm. Okay, that means to say slightly the output impedance gets reduced due to the effect of, you know, finite value of R0. Okay, so slightly it gets reduced. Okay, that means to say even your output voltage should also be reducing. Okay, let's see. Yeah. So this is your part A of fifth, and this is part B. AV with R0 is equal to 50 kilo ohm. Let's see how much you'll get the voltage gain. So voltage gain AV is basically minus RC parallel with RE, R0 divided by RE. Okay. So how much you'll get? Minus RC parallel with R0. Kilo divided by 10.71. How much you'll get?
263.3.
Minus 263.3.
3.
Okay, 63.3. So what is the conclusion for AV? By how many units the voltage gain has reduced? See, the earlier voltage gain was negative 280 and the present voltage gain is negative 263. So, you know, with R naught is equal to 50 kilo ohm, the voltage gain has, you know, dipped or reduced by an amount of roughly say 17 units. You can say by 70 units. Okay, why I'm saying units? Because voltage gain is dimensionless. Okay, so this is the problem. Okay, so each part can get you about say 2 marks each. So this will have 2 marks. Okay, and this will have 2 marks, and so as these 2 parts, 2 marks and 2 marks. Okay, so normally it will come for 8 to 10 marks. Okay, fine. So the same process is used throughout the circuit, whether it is RE model or H model. The same idea is used, okay, to determine Zi, Z0, AV, and AI. Okay, fine. Let me take a brief pause here. Just want to understand. Did you understand? Did you understand this?
Yes, sir.
Yeah, frankly, you should say. If you don't understand, you know, I can take a special class and I can redo the stuff. But I want proper confirmation from your side, whether you have understood or not, because I cannot see you from the other side, right? Because I can't see you whether you have really understood or not. Okay, I have to just believe your words. Okay.
Understood, sir.
Yeah, if no, please feel free to, you know, ping me. I can arrange for a special class. Okay. So can I have some yes or no in the chat box? If understood, yes. If not understood, I'll assume that you haven't understood. I can arrange for a special class.